Close your eyes and imagine farmland. What do you see? You see rows, endless, perfect parallel rows, stretching toward the horizon like lines on notebook paper. Corn in rows, wheat in rows, soybeans in rows. Even in your own backyard, you probably planted your tomatoes in rows, your lettuce in rows, your herbs in a neat straight line along the fence. We've been conditioned to believe this is what order looks like. This is what intelligence looks like. This is what separates us from the chaos of wild nature. But what if I told you that these rows, these perfect geometric lines we've spent a century perfecting, are slowly starving your soil, collapsing your yields, and fighting against 4 billion years of evolutionary wisdom? What if the most productive growing system ever documented doesn't look orderly at all? What if it looks like chaos? In the mountains of southeastern Brazil, there's a farm that shouldn't exist. The soil there was declared agriculturally dead in the 1980s, chemically depleted, biologically exhausted, the kind of ground where even weeds struggle. Yet today, that same land produces more food per square foot than the vast majority of industrial farms in North America. The fruit trees there grow faster, live longer, and yield harvests that make agricultural scientists check their notes twice. Water usage is 60% lower than neighboring properties. Fertilizer costs are essentially zero. Pesticide use is zero. And the farmer who transformed this land didn't use a single innovation from modern agribusiness. No genetic modification, no precision agriculture, no drones or sensors or smart irrigation. He used geometry. He used circles. He used a pattern that every forest on Earth has been using since before humans learned to plant seeds. His name was Ernst Goetsch, and when his neighbors first saw his yields, they didn't call him a scientist. They called him a witch, because the results seemed impossible. His system produced approximately 400% more food per square foot than conventional methods. 4 times the output from the same amount of land, water, and sunlight. Let that number settle in your mind. Not 4% more, not 40%, 400%. If someone told you they'd invented a new tractor that could quadruple your harvest, you'd think they were selling snake oil. But Goetsch wasn't selling anything. He was remembering something we forgot. Before we understood what Goetsch rediscovered, we need to understand how we ended up here in a world where the most unnatural growing pattern imaginable, the straight line, became synonymous with efficiency. For almost everyone alive today, farming has always looked modern, industrial, rational. We see photographs from the 1920s, the 1950s, the 1980s, and they all show the same thing. Fields divided into straight sections, crops planted in parallel lines, trees in orchards spaced with mathematical precision, forming perfect grids you could navigate with a compass. This wasn't always the human way. For thousands of years, farmers planted in curves, in clusters, in patterns that followed the contours of hills and the flow of water. They intercropped. They companion planted. They watched how wild ecosystems behaved and tried to mimic them. Then came mechanization. The tractor changed everything. Suddenly, the primary question wasn't what's best for the plants or the soil. It was what's easiest for the machine. Straight rows are easy to plow, easy to plant with mechanical seeders, easy to spray with industrial equipment, easy to harvest with combines that cost $500,000 and need 300 feet of turning radius. From an airplane, a modern farm looks beautiful, geometric, controlled. It looks like humanity has tamed nature, bent her to our will, imposed order on chaos. But here's the question we forgot to ask. Efficient for whom? Those straight rows are extraordinarily efficient if you're a John Deere tractor. They're incredibly efficient if you're a crop duster. They're remarkably efficient if you're a corporation trying to manage 10,000 acres with as few workers as possible. But if you're a plant, if you're soil, if you're the water trying to sink into the ground, or the insect trying to find habitat, or the fungus trying to connect root systems underground, Those straight rows are a disaster. They're designed against life. Walk away from any farm field and into wild land, into a forest, a prairie, a wetland, a meadow that's never been plowed. You'll notice something immediately. Nature almost never uses straight lines. Life curves, it spirals, it clusters in patches, it flows around obstacles, it creates mosaics of different heights, different species, different root depths, all occupying the same space. And most importantly, life concentrates at the edges. This is one of the most powerful principles in ecology, and somehow modern agriculture spent a century trying to eliminate it. It's called the edge effect, and once you understand it, you'll never look at your backyard the same way. Imagine you're standing at the border between a forest and an open meadow. Behind you, grassland, full sun, wind moving freely, a few scattered wildflowers. Ahead of you, towering oak trees, dense canopy, cool shade, the smell of decomposing leaves and rich soil. And right where those two worlds meet, in that narrow transitional zone where the forest begins to break apart into scattered trees and thick understory, something extraordinary happens. Biodiversity explodes. Ecologists have measured this over and over, in every biome, on every continent. The edge between two ecosystems contains more species, more biomass, more interactions, more productivity per square foot than either ecosystem on its own. Why? Because the edge blends conditions. There's enough sunlight for sun-loving plants, but enough shelter for shade-tolerant ones. There are tall trees providing structure, smaller trees filling the mid-story, shrubs creating habitat, herbs and flowers carpeting the ground, vines climbing upward, mosses spreading across bark. Roots reach different depths, accessing different nutrients and different water sources. Insects and birds use the edge as a highway, moving between the two ecosystems, pollinating, hunting, dispersing seeds. Beneath the surface, fungal networks connect the roots of different plants, allowing them to share resources and information. Bacteria break down organic matter and fix nitrogen from the air. The edge is not neat. It's not symmetrical. It doesn't look like a planner designed it. But it's astonishingly, almost violently productive. Modern agriculture looked at edges and saw problems. Hedgerows were ripped out to make fields bigger and easier to manage. Tree lines along property borders were bulldozed so machines could turn without obstacles. Streams were straightened into channels. Wetlands were drained. Every edge, every transition zone, every messy border between different types of land was eliminated in the name of efficiency. We replaced edges with rows. We replaced diversity with monoculture. We replaced living complexity with geometric simplicity, and we called it progress. Ernst Goetsch looked at those same edges and saw a blueprint. He didn't just want to preserve edges, he wanted to create them. He wanted to build entire agricultural systems that functioned like one continuous, regenerating edge. To do that, he had to understand the geometry. When you study natural edges closely, you start noticing patterns, specific mathematical relationships that appear again and again, spirals, branching patterns, ratios that govern how leaves arrange themselves on a stem, how seeds pack themselves into a flower head, how shells grow outward in elegant curves. Look at the center of a sunflower. The seeds aren't scattered randomly, and they're definitely not arranged in rows. They're organized in two sets of spirals, one curving clockwise, the other counterclockwise, interlocking like gears. If you count those spirals, you'll almost always find Fibonacci numbers. 34 spirals in one direction, 55 in the other, or 55 and 89, or 89 and 144. These aren't arbitrary numbers. They're part of a sequence where each number is the sum of the two before it. 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. This same sequence appears in nautilus shells, in the arrangement of pine cone scales, in the way ferns unfurl, in the branching patterns of trees and rivers and lightning. And if you divide any Fibonacci number by the one before it, you get a ratio that approaches 1.618, a number mathematically known as phi, the golden ratio. This isn't mysticism, it's not cosmic coincidence, it's optimization. The golden ratio and Fibonacci spirals represent the most efficient way to pack elements into space, without crowding, without excessive shading, without waste. When a sunflower arranges its seeds in Fibonacci spirals, it's solving a packing problem. It's fitting the maximum number of seeds into the flower head while ensuring each seed has enough room to develop. When a tree arranges its leaves in spiral patterns up the trunk, it's maximizing sunlight capture. Each leaf is positioned so it doesn't completely shade the leaves below it. Every pod gets its time in the light as the sun moves across the sky. Nature uses these spirals because they work. Because over billions of years, the plants that use this geometry outcompeted the plants that didn't. Gutsch realized that if nature uses spirals to maximize light, space, and resources, agriculture should too. So instead of planting in rows, he began planting in circles and spirals, creating structures that behaved like forest edges, no matter where they were placed on the land. Here's how you build one. Choose a point on your property. At that center point, plant a nitrogen-fixing tree. In temperate climates, that might be a Siberian pea shrub or a black locust. In tropical regions, it could be a gliricidia, a leucaena, an acacia. The specific species doesn't matter as much as the function. This tree's job is to pull nitrogen out of the atmosphere and pump it into the soil through a symbiotic relationship with bacteria in its root nodules. It's a living fertilizer factory. In the first ring around that central tree, perhaps 2 to 4 feet out, you plant more nitrogen fixers and what permaculturists call dynamic accumulators. These are deep-rooted plants like comfrey, chicory, dandelion, yarrow. Their roots plunge 6, 8, 10 feet down, reaching minerals that shallow-rooted crops can't access. They pull up calcium, potassium, phosphorus, trace elements, and concentrate them in their leaves. When those leaves fall, or when you cut the plants back, all those deep minerals become available at the surface. In the second ring, you plant fruiting shrubs, currants, gooseberries, blueberries, elderberries. These plants thrive in partial shade. They don't want full desert sun blasting them all day. They want protection, dappled light, moderated temperature. The taller plants in the center provide exactly that. In the third ring, you add herbaceous perennials, culinary herbs like oregano, thyme, sage, medicinal plants like echinacea, calendula, flowers that attract pollinators. These plants form a living mulch, covering the soil, preventing erosion, reducing evaporation, creating habitat. At the outer edge, in the fourth ring where full sunlight still reaches, you plant annuals, tomatoes, peppers, lettuce, beans, squash. The fast crops, the ones you harvest in a single season. They get the intense light they need, but they're also sheltered from wind, benefiting from the moderated microclimate the inner plants create. You've just built a circle, a guild, a self-supporting community of plants. But here's where the geometry matters. If you space those plants using Fibonacci spirals instead of grid patterns, something beautiful happens. As the sun arcs across the sky from dawn to dusk, the taller plants don't permanently shade their shorter neighbors. Each plant gets its moment in the light. Air circulates through the system instead of stagnating. The soil is protected from pounding rain and temperature extremes, but still gets enough light to stay biologically active. Leaves fall where they're useful. Roots interlace, holding soil together, creating channels for water. Fungi colonize the root zone, forming mycorrhizal networks that connect different plants, allowing them to trade sugars for minerals. Within a few years, the soil underneath that circle doesn't resemble the soil you started with. What was once compacted, dusty, lifeless dirt becomes dark, crumbly, sweet-smelling earth. Worms appear. Beetles, ground-nesting bees. The system comes alive. That's the forest edge. Secret. Not just planting trees. Not just mixing species, but planting them in the geometric relationships that forests have always used. There's another massive problem with conventional agriculture, especially tree crops, that Goetsch's system solves. The waiting. You plant an apple tree and wait 5 years before significant fruit. A peach tree, 4 years. A nut tree, 10 or 15 years. During all that time, you're pouring in water, fertilizer, labor, money. The young tree just sits there, growing slowly, producing nothing. For commercial orchards, those early years are pure cost. The land is occupied but not productive. For home gardeners, it's discouraging. You plant a fruit tree with excitement, then watch it do almost nothing for half a decade. Most people accept this as inevitable. Trees just take time. But Goetsch looked at those empty years and saw wasted sunlight, wasted rainfall, wasted opportunity. In nature, when a forest regenerates after a disturbance, a fire, a heat, hurricane, a landslide, it doesn't sit idle. It doesn't wait patiently for the climax species to mature. It floods the disturbed area with life immediately. Fast-growing pioneer plants rush in. Grasses, wildflowers, shrubs, fast-growing short-lived trees. They grow explosively, sometimes putting on 10 feet in a single season. They shade the soil, preventing erosion. They drop enormous amounts of leaves and organic matter. They change the microclimate, making it cooler, moister, more hospitable. Only later, after those pioneers have done their work, do the long-lived trees take over. The pioneers die back, get shaded out, complete their cycle, and their bodies become the soil that feeds the next generation. Nature doesn't plant for a single timeline. Nature plants in succession. Early species, middle species, late species, all occupying the same space but peaking at different times. Goetsch started doing the same thing with agriculture, a technique he called syntropic succession. Instead of thinking, I'm planting an orange grove, he thought, I'm planting a sequence of overlapping communities. In year 1, he would fill the spaces between his young fruit trees with fast-growing pioneers. In tropical Brazil, that meant bananas and papayas. These plants grow at shocking speed. A banana can go from a small shoot to a 15-foot plant producing fruit in less than a year. Papayas fruit in 6 to 9 months. They send up huge paddle-shaped leaves that create instant shade. They produce massive amounts of biomass. And critically, they produce food right away, generating income while the slower fruit trees mature. From the outside, a syntropic planting in year 1 looks chaotic. Plants are dense, almost jungle-like. There are multiple heights, multiple species, almost no bare soil visible. To a conventional farmer, it looks wrong, messy, amateur. But every single plant has a function. The bananas and papayas are shading the soil, protecting it from baking in the tropical sun, preventing the topsoil from eroding in heavy rains. They're capturing sunlight that would otherwise hit bare ground and go to waste. Their roots are breaking up compacted layers. Their leaves, when they fall, are thick, rich, full of nutrients. Underneath that protective canopy, the young mango trees, the cacao trees, the long-term fruit producers are quietly growing stronger, protected from stress, surrounded by abundance. By year 2 and 3, those pioneer plants have produced multiple harvests. They've reached full size, and now, instead of being permanent fixtures, they enter a different phase. Goetsch begins pruning them, not lightly, not just trimming. He cuts them back hard. Entire banana pseudostems, thick as your thigh, get chopped down. Papaya trunks, leaves, branches, everything. And here's the part that shocks people. He doesn't haul any of it away. He doesn't burn it, doesn't chip it, doesn't compost it in a separate pile. He lets it fall exactly where it grew. This is chop and drop, and it's one of the most powerful techniques in regenerative agriculture. All that biomass, hundreds of pounds of it, lands on the soil as mulch. It covers the ground in a thick protective layer. It breaks down slowly, feeding earthworms, beetles, fungi, bacteria. It insulates the roots of the young trees. It slows evaporation so the soil stays moist far longer after rain. It moderates temperature extremes, and as it decomposes, it releases a steady stream of nutrients directly where they're needed. Every 3 to 6 months, he repeats the process. The pioneers grow back from their bases or from seeds. More growth, more pruning, more biomass dropping onto the soil. Above ground, it looks like organized chaos. Below ground, it's a biological revolution. The soil transforms. Organic matter climbs from less than 1% to 5%, then 10%, then higher. Structure improves. Aggregates form. Pore space increases. Water infiltration goes from slow to rapid. Biology explodes. Fungal hyphae spread like neural networks. Bacterial populations surge. The soil becomes alive. When Gutsch began working degraded land in Brazil's Atlantic forest region, soil tests showed organic matter levels around 0.5%. That's catastrophically low. That's soil that can barely hold water, that crusts over when it rains, that depends entirely on chemical inputs to grow anything. After 2 decades of syntropic management, that same soil measured around 14% organic matter, from 0.5% to 14%. That is not incremental improvement. That is resurrection. At 14% organic matter, soil behaves like a completely different substance. It becomes spongy, able to absorb heavy downpours without runoff. It holds moisture through dry periods, meaning irrigation needs plummet. On Gutsch's land, water use dropped by approximately 60% compared to neighboring conventional farms. Trees grown in that kind of soil are stress-resistant. They handle drought better. They recover faster from pest damage. Disease pressure drops because healthy soil creates healthy plants, and healthy plants have strong immune systems. Pest outbreaks, when they occur, are shorter and less severe because the diverse ecosystem naturally balances predator and prey populations. And the yields don't just increase once. They keep climbing year after year because the system is improving itself instead of degrading. All of this without synthetic fertilizer, without pesticides, without herbicides, without GMO seeds. Just plants, arranged in space and time the way forests have always known to arrange themselves. At this point, you might be thinking, this is incredible, but it's for farmers, for people with acreage, for tropical climates. I have a suburban backyard in Ohio. I have 1/10 of an acre in Oregon. This doesn't apply to me. Here's what makes these principles so powerful. They scale down. You can compress the logic of a forest edge, the power of succession planting, and the geometry of syntropic guilds into something as small as a 6-foot circle in your backyard. Think of it as a pocket forest, a miniature guild, a tiny, self-supporting ecosystem centered around a single fruit tree. Instead of planting one lonely apple tree in the middle of your lawn, surrounded by grass you have to mow every week, you build it a community. You give it partners. You create conditions where it can thrive instead of just survive. Here's how you do it this weekend. Go to a local nursery and choose a dwarf fruit tree. For most of North America, a dwarf apple on M27 or M9 rootstock is perfect. It stays small, 6 to 8 feet tall, manageable without a ladder, but it still produces full-sized apples. In warmer climates, consider a dwarf peach, a fig, a persimmon, a plum. Pick something that belongs in your hardiness zone. Now build its support system. mark out a circle 6 feet in diameter. You can use a stake, a string, and some flour or spray paint. Remove the grass inside that circle. You can smother it with cardboard, dig it out, whatever works. In the center, plant your fruit tree. About 1 to 2 feet out from the trunk, in the first ring, plant chives and garlic chives. These aren't just kitchen herbs. Their strong scent confuses many fruit tree pests, particularly aphids and borers. Their flowers are pollinator magnets. You can harvest them repeatedly all season, and they come back year after year. They're also beautiful, with purple pom-pom flowers. In the second ring, about 3 feet from the center, plant strawberries. Not in a row, in a loose, organic arrangement. Strawberries spread by runners, forming a living carpet. They cover bare soil, choking out most weeds. Their roots stabilize the soil, and they produce fruit, often in the very first year, sometimes even the first season you plant them. On the outer edge of your circle, plant flowering plants that serve multiple functions. Calendula, marigold, borage, nasturtium. These draw in pollinators, bees, butterflies, hoverflies, beneficial wasps. Many have edible or medicinal properties. Calendula petals are anti-inflammatory and can be used in salves. Nasturtium leaves and flowers are peppery and delicious in salads. Borage flowers taste like cucumber and are stunning in cocktails. Look at what you've created in one afternoon. You've planted a fruit tree that will produce for 20 or 30 years. You've surrounded it with herbs you can harvest weekly. You've added a ground cover that produces berries. You've installed a pollinator habitat that will support beneficial insects all season. And you've started the process of building soil. Now mulch the entire circle heavily. Use shredded leaves, wood chips, straw, grass clippings, compost, whatever organic material you can find. Lay it down 2 to 4 inches thick, keeping it a few inches away from the tree trunk to prevent rot. Water everything deeply. And then, here's the hard part. Leave it alone. Don't fuss over it. Don't try to make it look like a magazine photo. Let plants touch each other. Let leaves fall and stay where they land. Let it be a little wild. Check on it weekly during the growing season. Snip chives for your eggs. Pick strawberries for your kids. Enjoy the flowers. When something grows too tall or flops over, cut it back and drop the cuttings right onto the soil. That's chop and drop on a small scale. You're feeding the system with itself. Over the next few months, you'll start noticing changes. The soil underneath the mulch stays cool even on hot days. It stays moist longer after rain. Worms appear. The tree puts on strong, healthy growth. By the second year, your strawberries will spread. Your chives will multiply. Your flowers will self-seed. You'll be harvesting something almost every week from spring through fall. And in year 3 or 4, your dwarf fruit tree will start producing. Not just a few apples. Dozens of them, maybe 50 or 60 from a single small tree. All of this from a 6-foot circle that used to be lawn. Now imagine you have room for 3 of these circles. Or 5. Each one is a different fruit tree with a different combination of companions. One circle around an apple tree, another around a pear, a third around a cherry. Each circle creates its own edge, its own microclimate, its own burst of biodiversity, and together they produce far more food with far less work than a traditional garden with rows ever could. The financial comparison is stark. A single dwarf fruit tree from a nursery costs about $30 to $50. Add a bag of bark mulch for $15. Add some granular fertilizer for another $20. You're at around $75 to $100, and all you get is one tree that won't produce fruit for years. Now compare that to the same initial investment in a guild. Dwarf fruit tree, $40. A 6-pack of strawberry starts, $10. A bundle of chive plants, $8. A flat of pollinator flowers, $12. Bulk mulch material, $20. You're at $90, and you've created a system that starts producing herbs and berries immediately, supports beneficial insects, builds soil, and sets up your fruit tree for long-term success. In 3 years, that single tree with bark mulch might give you 20 apples. The Guild will have given you dozens of harvests of strawberries, hundreds of chive cuttings, constant flowers, dramatically improved soil, and then, on top of all that, the same 20 apples from a healthier, stronger tree. The choice isn't even close. Rows are for machines. Circles are for life. For 10,000 years, humans planted in curves, in spirals, in patterns that followed water and wind and the shape of the land. We grew many species together because we understood, instinctively or through observation, that diversity creates resilience. Then came the industrial age. Then the tractor, the combine, the center pivot irrigator. Then the seductive idea that nature was something broken, something inefficient, something that needed to be fixed, straightened, simplified, controlled. We did grow more food for a while. We fed billions. But we also eroded topsoil faster than it could regenerate. We depleted aquifers. We poisoned rivers with fertilizer runoff. We created dead zones in the ocean. We lost forests, wetlands, prairies. We collapsed insect populations. We made our food system simultaneously more productive and more fragile. A strange paradox where we could feed more people, but only by depending on inputs that couldn't last, systems that couldn't sustain themselves, chemistry that came from fossil fuels. Now, as climate instability increases, as soil degradation accelerates, as the hidden costs of industrial agriculture become impossible to ignore, people like Ernst Goetsch are showing us another way. Not a new way. An ancient way. A way that works with the patterns life has been refining for 4 billion years. Goetsch's neighbors thought what he was doing was magic. Now you know it isn't magic. It's geometry, it's ecology, it's succession, it's working with edges instead of eliminating them, it's planting in time as well as space, and every single principle he used on his Brazilian farm can be applied in your backyard. You don't need 50 acres to try this. You don't need to quit your job and become a farmer. You need 1 fruit tree and a 6-foot circle of earth around it. You need a weekend, maybe 2 if you're starting from scratch. You need to stop thinking in rows and start thinking in relationships. This Saturday, if you can, go to a nursery. Bring this article on your phone if it helps. Choose a dwarf fruit tree suited to your climate. Pick up some companion plants, strawberries, herbs, flowers. Go home, mark your circle, plant your guild, mulch it deeply. Then let it be. Don't make it neat. Don't make it symmetrical. Let it be alive. Take a photo the day you plant. Then take another photo in 1 month, another in 3 months, another in a year. Watch how quickly life accepts your invitation. Watch how fast bare dirt becomes ecosystem. In 1 year, compare those photos. Look at your soil. Look at your harvests. Look at the bees and beetles and butterflies. Look at how 1 small circle changed the way you see your yard, your food, and maybe the way you see what farming could be. If you decide to share your journey online, others will see what's possible. The most inspiring transformations, the healthiest guilds, the most abundant 6-foot forests will encourage countless others to plant their own. This isn't just about growing tomatoes. It's about remembering how life actually works, how ecosystems build fertility instead of depleting it, how abundance comes from complexity, not simplification. Next week, we'll explore another forgotten principle, the plants that feed you while you sleep, perennial crops that produce year after year with almost no maintenance, the laziest and most productive gardening you've never tried. Until then, plant your circle. Let the rows belong to the machines. Let the circles belong to life.